Hey everybody, so this video is going to be chapter 6, lecture 2. So if you guys remember in the last lecture, we introduced the simple gas laws, right? Boyle's law, Charles' law, and Avogadro's law. So let's just quickly go over that real quick again. So the relationships, right, between two gas characteristics at a time where the other two are remaining constant. So remember, the four gas characteristics are moles, volume, pressure, and temperature, right? And all interrelated. So studying all four of them at the same time is really complex. And so that's why the early, scientists, they decide to just study two gas properties at a time and keep the other two constant. So if you remember Boyle's law, Boyle studied volume and pressure while keeping moles and temperature constant, right? And what he found was that volume was inversely related to pressure, right? So volume is proportional to 1 over P, right? So what does that mean? Volume goes up, pressure goes down. Volume goes down, pressure goes up, right? And then Charles studied volume and temperature while keeping moles and pressure constant, right? And what did Charles learn? That V and T are directly related, right? So as one goes up, the other one goes up as well, right? Volume goes up, temperature goes down, volume goes down. Right? And then Avogadro, he studied moles and volume, right? He also found that there's a direct relationship between the two. So as moles go up, volume goes up. As moles go down, volume goes down, right? So that's what we call Avogadro's law, right? So if we were to put all this together, right, and let me switch to the board at this point, it's pretty easier, right? So if you now combine all of this, what you get is volume is proportional to moles and temperature over P, right? Because volume is inversely related to pressure, but directly related to moles and temperature. So they go in the numerator. Okay. So now we start to get something that looks like, an overall equation for describing a gas, right? So let's keep going. I'm going to multiply P to both sides. So that would get PV is proportional to FT. Okay. And remember, in order to get an equation out of this and turn this into an equal sign, we will have to introduce a constant. Okay. So PV is equal to nRT. So notice that R is our constant. And this is called the gas constant. Okay. And this equation right here, PV equals nRT, or as I like to remember it, pervert. Okay. Makes it easier, right? You see that? Pervert. All right. This is called the ideal gas law. So that's what we've done is we use the simple gas law to derive the ideal gas law. What the ideal gas law does for you is if you know 3 out of the 4 gas characteristics, you can calculate for the fourth, right? So you see all 4 of the gas characteristics are in this equation and it's related by R. So let's talk about what R is. R has a value of 0.08206 liter ATM over K, which is Kelvin, over mole. Okay. So this is the gas constant, and I want you guys to remember the gas constant to 4 sig figs. Okay. So you should have that memorized. And also the units as well. So the units seems hairy until you realize where R comes from. So let's go back to ideal gas law. R is equal to, right? Let's isolate R. That means we're divide by N and T. So R is equal to PV over NT. Okay. So that's why you get this unit of liter atmosphere per K mole. Volume is measured in liters, okay? In this kind of equation, you want to keep volume as a liter. The pressure must be in ATM, okay? And the temperature has to be in Kelvin, that's on bottom, and then moles, okay? So that's why you want to memorize the units as well as the number associated with it, okay? So again, it's 0.08206 liter ATM per K mole. All right, so where does this number come from? Well, it's this ratio. For any gas, if you take its pressure, its volume, its moles, and its temperature, and you do this ratio of PV over NT, lo and behold, you always get this number, regardless of the gas. So R is a constant that just occurs in nature, and we know other constants. For example, pi, right? Used in geometry, pi is 3.1415. So this magic constant that kind of occurs everywhere, right? When we're looking at geometry, we're looking at like cycles and anything that's round, okay? Here, the magic number is 0.08206. It occurs every time we look at any types of gas and we take the PV over NT, okay? So that's how we get that value. So that gas constant now can serve as sort of a reference point, right? Remember, for two condition problems, let's say this was P1, V1, N1, and T1, then you should also get R for P2 and P2, V2 over N2, T2. Okay, so now what if you equate this? You'll get a master equation for two conditions. P1 over P1, V1 over N1, T1 is equal to P2, V2 over N2, T2. Okay. And that's really useful, right? These two here. So this is for two condition, right? So condition one, condition two, okay? And you just have to look at the problem. What is the problem talking about? Is it talking about P and V, pressure and volume, while moles and T are constant? Well, in that case, then you just cover this up. And what is your equation? P1, V1 is equal to P2, V2, right? That's Boyle's law. Okay. Now, what if you were just talking about, in the problem, you see volume and temperature only. Okay, so pressure and mole stay the same. So just cover up pressure and mole, right? Because they stay the same. And what do you have? V1 over T1 is equal to V2 over T2. Right? Whose law is that? I can do this. There we go. So, right, in blue would be Charles. Okay, you see that? Charles' two condition equation. All right, what if it's talking about moles and volume only while keeping pressure and temperature the same? So then cover up pressure and temperature, and what do you have? V1 over N1 is equal to V2 over N2. Okay, that's Avogadro's law, right? Okay, so that's the equation for Avogadro's law. So isn't that cool? You can see the simple gas law within the bigger ideal gas law, right? So use this master equation whenever you have two condition problems, right? Now, there are going to be two condition problems where three things are changing and only one stays the same. So let's say only moles stay the same. So what is your equation? P1 V1 over T1 is equal to P2 V2 over T2. Okay, so that makes it easier. By the way, this is one of the first equations, I believe, on your equation sheet. So from now on, you guys get equation sheets so that you don't have to memorize so much. There's a lot of equations, but you must memorize pervert, okay? That's not on the equation sheet. So that's the only one I really ask you to memorize because if you know pervert, you can derive all of these, right? So that, later on in your life, if you had to, you could derive all of these just by knowing pervert, okay? All right, so let's go back to the slides and do some problems involving the ideal gas law. Okay, so this one says, calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 Kelvin. Okay, so let me write all these down. We got volume, right? So I like to write down all the pieces of information, right? Because then it's right there for me to figure it out. 0.845 mole, so volume, calculate the volume. So we don't know the volume. 0.845 moles of nitrogen gas, right? What's nitrogen gas? Everybody remember that's part of Hofbrinkel. So make sure that you're gonna write N2, right? And not N, okay? So that's moles of N2. And then the pressure, 1.37 atm. Okay. And the temperature, 315 Kelvin. All right. Reminder, right? Because of what the value of R is, all your volumes must be in liters, temperature must be in Kelvin, and pressure has to be in atm. Okay. If they're not that, then you have to convert first. But fortunately, in this problem, they're all at the right unit. So how can you tell that this is a ideal gas law problem and not a two condition problem? Well, you read it, right? There was no condition 1 or 2. It's giving you values for 3 things, and you're asked to solve for the 4th. That's how you know you use PV equals nRT. And what is the one that wants us to solve for? Volume. So we need to isolate volume, right? So V is equal to, we should divide both sides by P to get nRT over P, right? Then you just plug it in, right? Moles, 0.845. R, remember what R is? You got to memorize that, right? 0.08206 liter atm per K mole, okay? Times the temperature, 315 Kelvin right there, okay? Divide by pressure, 1.37 atm, okay? So it's just plug and chug, right? That's the great part about this chapter. It's like, if you understand the equation, which one to use, just plug in the numbers, go, right? So now let's look at how the units cancel. This is a great spot to check yourself, right? To see if you actually solved you're setting up the problem correctly. If your units don't work out, then you know, okay, I probably didn't set up right. Okay, so do this part. Don't just go through the motion. Actually, verify that units will cancel. So ATM's on top, ATM's on bottom. That'll cancel. Look, Kelvin here's on top, Kelvin here's below, right? So Kelvin will cancel. Mole cancels on top, mole on bottom, right? And what do you have left on top? Liters, right? Because we are looking for a volume, right? So punch all that in, and you should get 15.9 liters, okay? 3 sig figs. Okay, and liters of what? We say liters of nitrogen gas, right? That's what it's asking for. Okay, so nitrogen is N2. All right, let's do the next problem. This one says, calculate the number of moles of gas in a 3.24 liter basketball inflated to a total pressure of 24.3 psi at 25 degrees Celsius. Okay, so calculate the number of moles. Okay. And then this note here, yeah, you guys can read that. It's not gonna really affect our problem here. So let me write all that down again. We got, now it's giving us a volume. Calculate the number of moles. So N is what we're looking for, right? You always want to orient yourself here. That's why I do this every time. Volume is 3.24 liter. Okay, like, okay, great. Volume's in the right unit. We got a total pressure of 24.3 psi. Okay, and we got a temperature of 25 degrees Celsius. All right, so question is everything in the right unit? That's what you need to verify first before you even plug it into an equation, all right? Are things in the right units? No. Pressure needs to get changed to ATM, right? From PSI to ATM. Temperature from Celsius to Kelvin, okay? So let's do it. PSI, remember the equivalency. This is on your conversion sheet, right? You don't have to memorize it, but you'll see that is 1 atmosphere is 14.7 PSI. Okay. And so that would be 1.653 ATM. Again, I'm leaving lots of sig figs, right? I don't want any rounding errors. Okay. So I don't want any rounding errors for sig figs, right? And then now I'm going to convert this to Kelvin. So 273.15 Kelvin. It's 298.15 Kelvin. And I'm going to underline, should be at the 8, right? Because it's 0 decimal place here when you're adding. So I can keep track of my sig figs, right? Okay, so we start from PV equals nRT. Again, how do we know it's an ideal gas law problem? Well, it gave us values for 3 things, and it's asking us to solve for a 4th, right? It's not a 2-condition problem, right? So you really need to orient yourself what kind of problem this is so that you're using the right equation, right? So PV equals nRT, we are solving for n. So n is equal to get n by itself, right? It means you have to divide RT to both sides. So PV over RT. Now, at this point, if you're like a little slow about it, you're not unsure, it's because you need to review your algebra, right? So go and review your algebra, or just practice like with these equations solving for P. Isolate P by itself. What is P equals to? What is V equal to, right? Or even R, what's R equal to? Just practice until you can get it very smooth, okay? Because that's actually the hardest part. After that, you just plug and chug, okay? Once you get that equation. So we got pressure, the ATM now, 1.653 ATM, and times by the volume in liter, which it already is, right? R, you know R, 0.08206 liter ATM per kmol. Don't worry, you're gonna memorize this number very quickly. You can use it all the time. And then temperature is 298 Kelvin. Underline that 8, right? So I see Kelvin cancels, ATM cancels, liter cancels, right? Top and bottom. And then what do we have left? It's a 1, right? 1 over a mole, which is the same thing as mole, okay? And that's what we want, right? We want moles out. So answer here. All right, this is 3 sig figs, this is 3, so we're gonna leave it in 3.219 moles of gas, right? Okay. Makes sense, right? Okay, let's go back to the slides here. See, we got it right. Yep, 0.219, good. All righty. So let's move on. So you guys know, now you can see how we utilize that pervert equation, right? The ideal gas law. It really is just plug and chug, pretty easy. Okay. Let's talk about now standard conditions. So standard conditions are a set of conditions that chemists have agreed upon in order to make it easy to compare gases all across the board, right? Because all gases behave differently. And also gases have different volume at different temperature and blah, 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 right? So to fairly compare them, we have to set conditions. So we call these standard conditions, or STP, stands for standard temperature and pressure, STP, right? So where we set standard pressure at is atmospheric pressure at sea level, which is 1 atm. Okay, that's pretty much where we are. Fairfield, or Vacaville and Fairfield are sea level, pretty much, right? So it's 1 atmosphere. Standard temperature, we're going to set at 0 degrees Celsius or 273.15 Kelvin. Right? So when we do that, something very interesting happens when we solve for a volume at standard temperature and pressure. So how do we do that? Well, let's just math it real quick, right? PV equals nRT. Solving for volume, V is nRT over P. And then we solve for 1 mole of gas, right? So N, we say 1 mole of gas times R, 0.08206 liter atm per K mole, times the temperature is 273 Kelvin, divide by 1, right? Pressure, standard pressure is 1 atm. What do you get? 22.4 liters. Okay, so for 1 mole of gas, the volume that gas occupies is 22.4 liters at STP. And what's interesting is it doesn't matter what the gas is. It will have the same number, okay? Which is interesting, right? If you think about it, what do you mean? It doesn't matter what gas it is, that 1 mole of gas is always 22.4 liters. That's definitely not the case with people, right? You have different people, they're not gonna take up the same amount of space. That's ridiculous, right? Everybody, in our class takes up a different volume. So what do you mean regardless of the gas? Well, that's the thing, right? We are solid state of matter. What is gas? Really far apart, right? Particles are super far apart. And so the individual volume of each gas particle is negligible compared to the overall volume of the container. So it's as if the gas does not have any actual individual volume, right? Here it's just measuring the entire gas that the gas occupies, right? Where it can fly to. And so that's why it can work that way, right? Whereas people, we're not like that, right? Our individual volume is big, right? So we can't ignore that. So interestingly, that's how it goes, right? It makes the math easier though, when you're calculating these things, because it doesn't matter if you have 1 mole of helium, 1 mole of xenon, or 1 mole of methane. At STP, they all take up the same amount of space. And what is that? 22.4 liters. Okay. So that's kind of another number that stands out that I like to memorize, or you just basically accidentally memorize, because it's so, you see it so often. Okay. So that's what we call molar volume at STP, 22.4 liters. Okay. Okay. So now let's talk about the density of a gas at STP. Go back to the board to derive this, okay? So the density of a gas at STP . Remember what density is. It's mass over volume. Okay. So density at STP, okay, you're going to take the molar mass of a gas, okay, and you divide by the molar volume. Remember what the molar volume is? 22.4 liters per mole, right? So how do the units work out? Let's see. So on top is molar mass. Remember what the units of molar mass is? It's grams per mole. So if you have grams per mole over 22.4 liters per mole, right? Notice that moles cancel. And so what do you have left? Grams over liter, mass over volume. Okay. So a density, okay, the density of any gas at STP is taking its molar mass divided by 22.4. Okay. So let's go back to the slide here. Notice that if you want the density of helium at STP, what do? You take its molar mass, which is about 4, right? 4.00, and you divide by 22.4 liters per mole. So what do you get? 0.179 grams per liter. Okay. You can do the same thing for nitrogen gas, right? Nitrogen is a diatomic gas, so N2. Therefore, its molar mass is 28.02 grams per mole. You divide by the molar volume at STP, which is 22.4 liters per mole, and you get 1.25 grams per liter. Okay. So if you compare the density of helium and nitrogen, guys, you guys see that it's a lot less dense than nitrogen. Okay. So that's interesting, right? That's how it works for a gas. It's all dependent on the molar mass, right? So the lighter the gas is, the less dense it is also, right? And the heavier the gas is, the more dense it is. Okay. Um, and that's a lot, right? 1.25 over 0.17. That's like what, 5 times more than 6 times more dense than nitrogen, right? And so that's why helium actually floats, right? So you have a helium balloon, it's going to float, right? Because nitrogen, which makes up most of our atmosphere, is so much more dense. All right. So now let's look at how density is related to molar mass, right? And so if we want the density not at STP, how are we going to derive that? Let's go back to the board. So we're going to derive it from PV equals nRT. Okay. So I'm asking you guys, all right? So we want density from this. Remember, density is a mass over a volume. In PV equals nRT, do you see something similar? It's not a mass over volume, but I do see a volume. I don't see a mass, but I see something that relates to mass, which is moles. So let's solve for that, right? Solve for N over V. N over V is P over RT. Okay. And now I have to figure out how to get M over V on the left side. So what is moles? How is mole and mass related? So if we take mass over molar mass, don't we get moles? Okay, isn't that how we do it, right? We want to convert from grams to mole, we divide by molar mass, right? Okay. So I can now substitute N as M over molar mass over V is equal to P over RT. Okay, so that was N, right? And so now I have an M over V, don't I? Okay. But then molar mass here is at the bottom, so I should multiply it and bring it to the other side. So that's going to get me mass over volume is equal to pressure times molar mass over RT. Okay. And so now I have basically derived the density equation for any other given time, not just at STP, right? So at any time, if I take pressure times molar mass divided by RT, I will get the density of the gas. Okay. All right, so back to our slides. Right, so that's the equation. Well, they use a fancy M here. You guys know I always use big M, molar mass, just more clear. Okay, this equation, any of these equations that we're deriving now, are on your equation sheet. So you should go and take a look at it. It's on Canvas, very bottom, just so that you get used to using it, right? Or you can see what kind of equations are given to you, so you know that you don't have to memorize those, right? And everything else that's not on there, then you know that you need to know it yourself, right? Okay, so from here, what you can do is also solve for the molar mass. Sometimes a problem, will ask you to solve for the molar mass of an unknown gas. And that's actually really, it's a real world problem. Just imagine you're in the lab and you get an unknown sample that you can measure its temperature, its volume, and all that. You can mass it, right? And at the end, you can get the density of this gas, or the molar mass of this gas, right? Those are very useful things, right? So once you have a molar mass of the gas, maybe you can take a jab as to what gas that is, okay? So how do you solve for molar mass? It's from the density equation, right? So just now isolate M by itself. So you're going to multiply RT to both sides. So you get DRT is equal to pressure times molar mass. Then you divide by pressure to get molar mass. So molar mass is what? DRT over P. Okay, that's also on your equation sheet. Okay, so D stands for density, right? Or you can think of it, if you break down density, then it's M over V, right? So then it becomes MRT over VP as your molar mass. All right, so let's do an example problem. It says, calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeter mercury. So nitrogen gas, what temperature? T is equal to 125 degrees Celsius. Pressure is 755 millimeter mercury. Okay. And then we are asked for the density. Okay. All right. So what is the density equation? So I have the molar mass one up there. We just need to solve back for D. So D is pressure times molar mass over RT, right? But remember, because you have R here, all of your units now need to be in liter, Kelvin, right? And ATM. This is not an ATM, so we need to convert to ATM. And remember, the equivalency is 1 ATM is 760 millimeter mercury. Right, so we have to divide by 760 to get that into ATM. Keep lots of sig figs, so 0.9934 ATM. That's your pressure. Oh, your Celsius needs to be in Kelvin. So you got to add 273.15. That's 125 plus 273.15. 398.15. Okay. All right. So now you can just plug it in, right? D is equal to pressure times molar mass over RT. Pressure is 0.9934 ATM. Times the molar mass of nitrogen gas. Got to remember that nitrogen gas is N2. Okay. What's the molar mass of N2? 2 times 14.01, 28.02 grams per mole. So 28.02 grams per mole. Divide by R 0.08206 liter ATM per K mole times the temperature, which is 398.15. Kelvin cancels, ATM cancels, mole cancels. Ooh, and what do we have? Grams over liter. That's a mass over a volume unit, right? Because we're being asked for density. Okay, so that's nice. Okay, always check your units cancel so that you know you're on the right track. Three sig figs, because I just underlined that, right? Yeah. And we also started out with 755. Yep. So 3 sig figs, 0.852 gram per liter is the density. Okay. Grams over liter, right? Okay. See if we got the right answer there. Yay. Alrighty. More practice for you guys here too. You should do it. All right. This next problem is going to ask us to solve for molar mass of gas. So you can see how we use that equation. See what I mean? This whole chapter is like plug and chug. Really easy. All you need to figure out is which equation to use, right? That's why you read the problem carefully, see what it's about. Here it says a sample of gas has a mass of 0.311 grams. If the volume is 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 886 millimeter mercury, what is its molar mass? Okay, so let me write all this again on the board and then we'll solve it together. So we got sample of gas has a mass of blah, blah. So mass 0.311 grams. Volume 0.225 liters. Temperature 55 degrees Celsius. And pressures 886 millimeter. Okay, find the molar mass. Okay. Molar mass formula, dRT over P. D is density, right? Do we have the information to get density? Remember, the density here should be in grams per liter, right? Remember, the volume should always be in units of liter. So we have it. Look, we have mass over volume here, right? So we just take this, divide by that, get density. The density is mass over volume, so 0.311 grams over 0.225 liters. Let's get that value. Yeah, 1.382 grams per liter. Okay, so yep, keep many sig figs because you're not done yet. And we go molar mass is equal to dRT over P. So density is 1.382 grams per liter times R 0.08206 liter ATM per K mole times temperature. Oh, our temperature is not in Kelvin yet, so we really need to convert that. 328.15 Kelvin, right? So 328.15 Kelvin. Divide by pressure. Our pressure is not in ATM yet, so we convert that by dividing by 760, right? Do it. 1 ATM on top, 760, and then H2 on the bottom. So that'll give us 1.166 ATM. Again, keep a lot of sig figs, right? 1.166 ATM. That goes on bottom here. Okay. So let's check that our units are going to cancel out and leave us with a molar mass unit, because that's what we're trying to find. ATM cancels. Liter C cancels. Kelvin cancels. And I think that's it. And then let's see what we have left over. We have a gram over mole. Wow, look at that. What is that? Gram over mole is a molar mass. Right? So we know we got this problem set up correctly. Let's punch it in. $31.9. But we do 3 sig figs, right? Grams per. Okay. Can we estimate, right? So we know this is the molar mass of this unknown gas. With it, can we kind of guess which gas it is? What gas has a molar mass of 31.9 or something close? Maybe 32. What gas has a 32 grams per mole molar mass? Perhaps O2. Okay. Each oxygen is 16. Okay. So you see how useful that is, right? These equations and what you're able to actually do in real life, right? You can actually do this, right? You have a lab, you know how to use all the instrument, just measure the temperature, measure the pressure, measure the density, and you'll get the molar mass of this gas. Okay. And then you can potentially figure out what it is, because there's not too many gases on the periodic table, right? Everything's mostly solid state, right? Very few are gas states, so you have a pretty good chance. Okay. Right, let's go back to our slides. Okay, let's get to now mixtures of gases. So far we've only considered, one gas and how one gas behaves, right? It's all flying in random direction and then it strikes the wall, and that's what gives rise to pressure and all of that, right? And then we see, how pressure, volume, temperature, and moles relate to each other. Okay. In mixtures of gases, now you put in more gases, right? Either one or two or three or four, sometimes even 20. Like the air that we breathe probably has about 20 different gas, right? But the main ones of the air we breathe is nitrogen gas, which is present in 78% total, right? Of the total. Oxygen gas is present in 21%. That's the one that, keeps us alive, right? We need that. And then we got argon gas, which is 0.9%. Carbon dioxide gas at 0.04%. So how these gases, they actually don't interact with each other because they are going so fast, right? They travel so fast that they just collide with each other and then go on their merry way. So even though they're present in the same container, they actually don't interact with each other. So they mainly act as if they are by themselves, which means that the math becomes really simplified, right? If you think about each gas is kind of acting on their own. So this is what we call partial pressures. So in partial pressure, each gas in the mixture exerts that amount of pressure, right? Based on how much of that gas is there, right? So if partial pressure is measured as the force of the gas striking the wall of the container, if you have more representation of the gas, then of course it's going to have a higher partial pressure, right? It's going to contribute more to the total pressure. So if you look at, say, the composition of dry air, because nitrogen is present in the most amount, of course, it's going to exert more force and therefore contribute to a higher amount of pressure than the rest of the gases, right? And so you would expect that the partial pressure of nitrogen gas is the highest, right? And by how much? Well, by exactly the percentage that's there, okay? So if, let's go back to the board here. So it's pretty intuitive. I mean, atmospheric pressure, right? The total atmospheric pressure is 1 atm, okay? So if the mixture of gases in the air is mainly nitrogen and exactly 78%, so the fraction, right, or the decimal is 0.78, 0.78 of 1 atm is 0.78 atm, okay? So that makes sense. So what we're saying is the partial pressure of nitrogen gas is 0.78 atm out of the total of 1 atm. Makes sense because nitrogen is present in the most. Okay. And then oxygen, you want to calculate partial pressure of oxygen, it's 21%. And 21% of 1 atm is 0.21 atm. Okay. And then you do that for argon. Partial pressure of argon is 0.009 times 1 atm. So 0.009. You do it for CO2. Now you get 0.0004 times 1 atm is 0.004. Okay, so these are the partial pressures of each of the components, the main components of air. You see that the one that's present the most contributes more to the total pressure, right? It makes sense. So if you add these all up, that's 1 atm, right? So that's how mixtures of gases work, right? They act independently of all the other gases. They still contribute the same amount of pressure as, however many particles are present, okay? Okay, so now we can just use logic, right? Since it's pretty intuitive, we can just now use logic to figure out some partial pressure equations that can be useful to us for calculations. So, I like to derive for you guys, right? And I hope you like it too, because I think derivations help you understand where things come from, right? And so it's not just mumbo jumbo of equations. It's like, oh, that equation makes sense, and that'll help you pick the right equation, okay? So I really are appealing to you guys to understand, try and not just plug and chug, try to really understand what each equation is. And so that's going to help you pick the right equation, and therefore the plug and chug is correct, right? So don't just blindly plug and chug, okay? That's not going to work. So in deriving all of these equations that I circle, which are the ones that you're going to use a lot, okay? We start with a very simple equation, right? The total pressure of a gas mixture is the partial pressure of each of the components of the gas within the mixture. So we call that partial pressure, right? So the P total is partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and so on and so forth, depending on how many gases are in the mixture, okay? But then remember that from PV equals nRT, the partial pressure of gas A is equal to moles of A times RT over V, right? This is coming from PV equals nRT, right? And we're just solving for P, right? So P is nRT over V. But if we only want to know about the partial pressure of gas A, then we only count the moles of A. Does that make sense? So just moles of A times RT over V. Okay, so once we have that, we can expand on this top equation here. So partial pressure of gas A is moles of A times RT over V plus partial pressure of B, which is moles of B times RT over V, plus moles of C RT over V, okay? And so on and so forth, okay? And then to get from here to here, you see that RT and V, they're all the same values. Why? Because all the gases are in the same container, so they're all at the same temperature, they're all at the same volume. I don't need to say TA and VA, TB and VB, they're all the same, right? So that's nice, because now I can just take RT over V and factor it out, right? So if I factor it out, this is what I get. P total is equal to moles of A plus moles of B plus moles of gas C times RT over V. Well, what does this mean? That's just the total number of moles. So I get this nice equation. P total is equal to moles total RT over V. Okay. So you see how these two equations are kind of similar looking, right? Because these gases are still behaving ideally, right? So you still get, N RT over V, basically. Okay, so now what's interesting too is if you take the ratio of the partial pressure of gas A over the total pressure, right? That should give you a fraction of gas A. What is this fraction? Well, let's calculate it. PA is NART over V. P total is N total RT over V. But RT over V cancels, right? So all the same values. So what you get is moles of A over mole total. Okay. And this is what we call a mole fraction. A mole fraction is the mole of A divided by the total number of moles. And that's denoted by this symbol chi. Okay, so I want you guys to remember that. Chi is the Greek letter that looks like this X. It's not an X. See how it's like curly Q like that? Draw it like that. It's called chi. So chi A is the mole fraction of A. And to calculate it, just take moles of A, divide by the total, right? Just a mole fraction. Right? So from this same equation, right? Remember earlier, PA over P total is NA over N total. You can also get a different partial pressure of A equation. Okay, so now partial pressure of A, you can also calculate by taking mole fraction of A times the total pressure, which makes sense, right? Whatever fraction of A is times the total will give you just the partial pressure of A. Okay, so these four equations, guys, that I have circled here, very useful when you are solving problems that involves mixtures of gases. They're on your equation sheet. Remember, you just have to know how to use them. Make sure you understand it. All right, so let's go back to the slides. Let's do some problems here. It says a 1.0 liter mixture of helium, neon, and argon has a total pressure of 662 millimeter mercury at 298 K. If the partial pressure of helium is 341 millimeter mercury and the partial pressure of neon is 112 millimeter mercury, what mass of argon is present in the mixture? Okay, let me take notes on the board, and then we'll work it out. All right. 1 liter mixture of helium. Okay, so the volume is 1 liter. Just taking notes. The mixture has helium, neon, and argon in it, and the P total. All right, so P total would be the partial pressure of, there were 3 gases in there, right? Partial pressure of helium plus the partial pressure of neon, Ne, plus the partial pressure of argon. And that has a total pressure of 662 millimeters. Okay, right? So, and then our temperature is 298 Kelvin. And then it gives you the partial pressure of helium. Partial pressure of helium is 341 millimeter mercury. Partial pressure of neon is 112 millimeter mercury. And now it's asking us for what is the mass of argon present in the mix. Okay. All right. So there we have it, right, guys? Okay. P total, right? We have three gases in the mixture. Since P total is 662 millimeter mercury, and then it gives us the partial pressure of helium, and it gives us the partial pressure of neon. That's great because we do need to know the partial pressure of argon, right? And we can do that. So how do we get the partial pressure of argon from this equation? Partial pressure of argon is taking the total, right? Subtracting out the partial pressure of helium and subtracting out the partial pressure of neon, right? So let's plug that in. The total is 662 mmHg minus partial pressure of helium is 341 mmHg, and neon is 112. Okay, right? The total is the sum of the parts, right? That's all. That's how you reason this, right? Total is the sum of the parts, and it gave us helium and neon's numbers, so we can subtract it out. So the partial pressure of argon is 209 mmHg. Okay. And then now it's asking us, let's orient ourselves. We have the partial pressure of argon, but it doesn't want that. It wants mass of argon. So what's related to mass? It would be moles, right? So we know we need to get to moles of argon first. So how do we get from a pressure to a mole? Guys, What is our equation that we just learned? Perfect, right? Because perfect has pressure and moles in it, right? So from PV equals nRT, we need to solve for N because we want to know how many moles of argon that is. So N is equal to PV over RT, right? We have to divide out RT. Okay. Now, remember, whenever you use ideal gas law, all your pressure has to be in ATM. So let's get this to ATM first. Right? 760 mmHg on bottom. Yeah, 0.275 ATM. For pressure, our temperature was already in Kelvin. Awesome. Our volume's in liter. Great. So we only had to convert that. Okay, so now we plug it in. 0.275 ATM for pressure times volume is 1 liter, right? Divide by R, 0.08, 206 liter ATM per K mole. Times the temperature, 298 Kelvin. Okay, so now we can knock out liter, ATM, Kelvin, and it's 1 over 1 over mole, which is the same thing as moles. So I get 0.01125 moles of argon. Right? You guys following, right? We just solve for moles of argon. But it doesn't want mole. What does it want? What is our problem? What? The mass of argon. So just one more step. How do we get from mole to mass? Molar mass, right? So 1 mole of argon on bottom. Okay. And then the molar mass of argon. Add up. 39.95 grams of argon on top, right? So moles of argon. This is 0.449 grams of argon. 3 sig figs, right? Looks like everywhere that we've been doing. Yep. Okay. Okay. So in this problem, right, mixtures of gases, it uses a couple concepts that you have to be well versed in, right? So first, it's the mixtures of gases. You know, you have to subtract out the other components to get to the partial pressure of argon, and then you needed PV equals nRT, right? That was the second concept, was to relate pressure to moles, right? Okay, and moles is something that we always want in chemistry, right? Can you guys notice that, right? So to be able to get from someplace else to mole, just like on your roadmap, is a very important thing, right? And something that you should have as like in your toolkit, right? So PV equals nRT is now allowing you to get to moles from 3 more different places. What are the 3 more different places? From pressure, you can get to mole. From volume, you can get to mole. And from temperature, you can get to mole, right? Which at first doesn't seem very intuitive, does it? Like, I have a pressure, how am I gonna get it to moles? What's a gas? So what do you use? Perfect, right? Or like one of the other ones where that's not as obvious to me, I remember as a student, was going from temperature to mole. I'm like, how the heck does a temperature rate to a mole, right? It's not as obvious, like, I know a mass, so I can get to mole. Temperature to mole, so again, wait a minute, it's a gas, isn't it? So what do I use? PV equals nRT, right? You know, unfortunately, you can't do that with solids, right? Temperature of a solid has nothing to do with its mass or mole, right? But a gas does, right? So if you have a temperature of a gas, you can get to moles too, right? Because usually you'll be given pressure and volume. Right? Okay, so keep that in mind, right, guys? You have more ways to get to moles now. Okay. Let's go back to slides. Okay. Hey, back to deep sea diving. This is really cool. One day I want to go and get certified. Um, but remember we were talking about every time that you go down like 10 meters, you'll experience like 1 atmosphere of additional pressure. So that when you're diving, you need oxygen tanks, right? In order to breathe, because down there, when you're at like 2 or 3 atmosphere, doing like this, just breathing in is not even feasible, right? Because your lungs are not used to being able to suck in 3 atmosphere. Like there's no way you don't have the suction power, right? So that's why you have to use a tank. Okay, so the tank can deliver you oxygen, right, at different pressures, right? So you can regulate the tank to give you, certain atmosphere as needed, depending on the depth that you're at. So on the surface, you're only breathing 1 atm, right? So the partial pressure of nitrogen you're breathing is 0.78, and partial pressure of oxygen you're breathing is 0.21 atm, right? But now if you're at 30 meters, your total pressure is 4 atm. And there's no way you can breathe by yourself. So you have this tank that is pressurized, that basically pushes the air into your lungs. And you're getting 3 atmosphere roughly of nitrogen. You get 0.84 atmosphere of oxygen, which is great because like that's 4 times the amount that you need of oxygen. You probably get high. You guys heard of these like oxygen bars that people go to, right? Where like they just like hook you up with the tubes and they just deliver you like just oxygen. It's like catnip to a human. We're like, oh, oxygen, so like probably get high off of that. But anyways, the optimum range that you want for oxygen is between 0.21 and 1.4. Okay. So this is safe, right? So 0.84 ATM that the tank is pushing in you're pretty safe. That's good. But if it goes over that, you get oxygen toxicity. Have too much oxygen, right? And so too much oxygen is like you get all woozy, you get all confused. I mean, you get too high, I guess. And then you get all, just not a good thing, right? You get really, really disoriented. Of course, if you have too low, you suffocate, right? We know that. That's called hypoxia, right? But you can also get too much. So what that means is when they create these mixtures in these tanks, they have to think about it, right? And like, look how much nitrogen you're getting too. 3 atm, that's a lot. So you can also have nitrogen toxicity, right? Not just oxygen toxicity. So that's why, for certain, mixtures, they try to add other gases in there so that the amount of nitrogen is not too much or the amount of oxygen is not too much, right? So they dope it usually with helium, right? Because helium doesn't do anything to you. It just makes you talk like, Mickey Mouse. Um, well, that's fine, right? You don't even talk underwater. So trimix, oxygen, nitrogen, helium is often used, or heliox. They put out the nitrogen completely because nitrogen toxicity is really bad, especially if you're underwater. You get like the bends and like you can't swim, like you get disoriented again, where you get really sick. So heliox just, you know, completely just gets rid of nitrogen, right? And so you don't have that issue. But then probably you have to worry about oxygen toxicity, right? Like getting too much oxygen here. But maybe they just, put in a lot of helium and your body's like, whatever, helium. So pretty cool, um, to think about these gas mixtures, right? All right, let's do this next problem. A 12.5-liter scuba diving tank contains a heliox mixture made up of 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate the mole fraction and the partial pressure of each component in the mixture and the total pressure of the mixture. Okay, this is a lot, so I'm going to take a bunch of notes again. So our volume, 12.5-liter scuba diving tank. We have 24.2 grams of helium in the tank. 4.32 grams of oxygen in the tank. And temperature is 298 Kelvin. Okay, now it wants to calculate mole fraction. So mole fraction of helium and mole fraction of O2. Okay, and that's what it wants. It also wants the partial pressure of each. So it wants the partial pressure of helium and the partial pressure of O2. And then finally, it wants the total pressure of the mixture. So it also wants to know what is P total. Okay, I think I got everything. Okay, so there we are, right? This is the situation. This is what it wants. Okay. So with mixture of gases problems, you don't really need to do anything in order. There's no like steps, like 1, 2, 3, like the roadmap, right? It's just what is the information that you see, and you reason it out, like what would make sense to do first? Like what is the information I have that I can do first? Okay. So let's see, it's asking for mole fraction, it's asking for partial pressure and total pressure. So remember our equations earlier, right? Let's look at the boxes, right? And then look back at the information you have. Which one would make sense to do? We have mole fraction equation, we have P total, right? Which we're gonna use eventually. Then we got two partial pressure equations, which we are also asked to do. Well, from what we have, I would say it makes sense to try to get mole fraction first, because we have the information for these, right? Mole fraction is mole over mole total, mole of that gas over mole total. Well, we don't have moles, but we have grams, right? So we can change these to moles, and we can get the mole total. So let's do that. Yeah, 2.42 grams of He. Let's do 1 mole of He on top. 4.003 grams of He on the bottom. Get that number. .6045 moles of He. Do the same thing for oxygen. So 4.32 grams. Oh, oops, that's 24.2. Sorry, wrote it down wrong. So 24.2 divided by 4.13 decimals here. 6.045. Yeah. 6.045. Good. All right, and then do the same thing for O2. 1 mole of O2 is 32 grams. 0.135 moles of O2. Okay. So we have moles of each, right? We just need mole total. So we add these together. 6.18 moles total. Okay. So now we can get pi of helium, right? Pi of helium is moles of helium over moles total. So moles of helium is 6.045 divided by 6.18. 0.9782. Okay. Helium, right? That's the mole fraction. And I can also do it for O2. So moles of O2 over moles total is 0.135 over 6.18. Right? Remember, these are mole numbers, so that's why the unit, right, gets canceled. So it's not moles anymore, it's just a fraction. Right? So this is 0.02184 for O2. Okay, so cool. We found this, right? So circle it. Right. Now we have this left. P helium, PO2, and P total. Of those three, you know what will make sense to do next? Look here. I just got chi. I just got moles total. If I have moles total, I can find total pressure. So let's solve for P total. Right? So you see, it's not like you just there are no steps. It's just like, oh, what information do I have, right? And what do I do using that information? So P total is N total RT over V. N total is 6.18 times R, 0.08206 liter ATM per cable times the temperature, which is 298 Kelvin. Okay, divide by volume, 12.5 liters. Okay, you guys can see. Okay, so liters cancel. Kelvin cancels. This was moles, right? 6.18 moles, so mole cancels. And I'm left with ATM, right? Great, because that's the volume, that's the unit of pressure. So let's punch that in. Well, if I do 3 sig figs, then 12.1 ATM. Okay. Okay. So that'll be the P total answer. Okay. So now that I have P total, I can get partial pressure easy. Remember this equation? Partial pressure of A, right, is chi of A times P total. Okay, I already solved for chi A. But at this point, you realize you could also use this equation because you already have moles of A. Right? So which one you want to use? Just which one's easier? I think this one's shorter. So let me use this one. But if you want to try and use this equation, it'll turn out to be the same thing. Right? So it's actually really cool that you have options so you don't need to follow certain steps. But I think sometimes that also it's daunting for people too, because like, oh, what do I do next? Like, I need my steps. It's like, no, here you have to really understand the problem, right? So try to, reason it out, right? So that's why I do encourage you to look at these equations, make sure it makes sense to you, right? Not just randomly plug things in, because that's not going to work for this part, right? Make sure something else. Well, for all parts, but yeah. So sit with the equations, make sure it makes sense to you, right? So you know how you use it. So I'm going to use P of helium is equal to chi of helium times P total. So chi of helium was 0.9782. Total is 12.1. I'm actually going to try and use, more sig figs. So I look up back on my calculator because I don't want rounding errors for here, right? So it was like 0.09. I get 11.8, right? For partial pressure of helium. And I can do partial pressure of O2. It's chi of O2 times V total. So that's 0.02184 times 12.9. Now give me 0.26. 264 because I want 3 sig figs. Okay, so if I add these two numbers, you can see it should become 12.1. Okay. Okay. So we got all the 5 things that we were asked for. Okay. Makes sense, right? Okay. So mixtures of gases. Study these, okay, and make sure that you understand them. It always tends to throw people off. It's the mixture of gases. People like they do PV equals nRT fine, but like when it comes to this, there's a little bit more trouble. So spend more time on it. You know, historically, it's a little bit challenging. Okay? And of course, let me know if you guys have questions. All right, I think that's it. Yep, for the second lecture. So I'll see you guys next time.